We need the. Oh, there he is, right there on the.
Ludwig Lorenz.
Yeah. What did he do?
Ludwig Valentines Lorenz, Danish physicist, mathematician, developed the mathematical formula to describe phenomena such as the relation between the refraction of light and the density of pure transparent substance, and the relation between the metal's electrical and thermal conductivity and temperature. The Wiedemann-Franz-Lorentz law. Let's look at that real quick.
Okay. What?
So, hard to read this. Temperature horizontal.
Yeah.
You have the resistivity
Yeah.
in watts per kilometer.
Wait.
Or
Watts.
ohm meters.
Watts per kilometer. Wait.
Resistivity in ohm meter. And a second one, which is lambda watts per kilometer.
Okay. So for a standard
second.
Okay, so it's like watts per kilometer is how much energy an electric current flow loses per kilometer, the rate at which that energy is lost.
The
That's
power,
a watt
yeah.
per kilometer. Yeah.
The power per kilometer. Okay.
Okay. And that's for a standard cross-sectional area. Okay.
Sure.
And the cyan is Lorenz.
Okay.
Which is wildly different than rho times lambda. And then what the hell's green? What is green?
Lambda is green. Rho is red. The multiplication of the two is the blue. And Lorenz is cyan.
They look so different. What am I looking at?
I mean, I see what red times green is. It's blue.
Yeah, it's blue.
But I don't know why cyan is on this.
So what the Wiedemann-Franz-Lorentz law is the cyan, which is important.
Lorentz number is more or less constant.
Oh, it's constant.
Yeah, more or less. I mean, its resistivity is not so temperature dependent.
I see. That's a lot for a law. Come on now.
Also, wait, Kelvin. So room temperature is here.
Here.
I guess it gets pretty cold. I mean,
so
100 Kelvin.
In the high temperature limit, it's very constant.
Yeah, which is very different than superconducting limit where your work was done.
Yeah.
Very different.
Just if it's take the limit, if it's constant, you got a law.
Okay. Let's also read it this way. In physics, the Wiedemann-Franz law states that the ratio of the electronic contribution to thermal conductivity kappa to the electrical conductivity sigma is of a metal is proportional to the temperature T.
How are they separating out?
And then the constant, the proportional constant is Lorenz number.
Okay.
Oh, cat. So here's this behavior. If one goes up, the other one goes up, and then you can get a constant temperature. And there's a prefactor, a constant, and Lorenz is like, that's mine.
Wait. So it's the top. The numerator is the electronic contribution of the thermal conductivity to the So there's the electronic contribution to thermal conductivity. How would you measure that? You're measuring thermal conductivity, and you're like, that's electron only, and that's other things. That's phonon. That doesn't count. Like, how are you separating this?
Oh boy.
How? It's not like I put in electric heat, specific heat only for electrons to travel through the material. How am I separating that out? What the heck?
States that the ratio of the electronic contribution of the thermal conductivity.
How?
So yeah, I think you've hit it right. So there's phononical thermal conductivity and then electronic. And so I guess you apply a temperature differential.
Okay.
and then from A to B, like left to right,
Yep. Yep.
and then you apply a voltage left to right versus right to left,
Okay.
and so then you can see the electron flow is going in different directions, and then you can see how fast that thermal separation, the hot to cold flows. Maybe.
Oh my gosh. So how? But
Experimental genius.
that's a really good idea. I wouldn't be convinced though that the electron current drift velocity would have to be equal to the rate at which heat flows in.
I guess it would be whatever the difference is divided by 2, and there's the electronic contribution.
I don't like it. I don't like it.
I don't
It's a
know.
good
I mean,
idea.
I don't know. Let's do
But
the experiment, see what comes out. I don't know. See.
it's okay, but it seems like a theorist wants to measure the electronic contribution to thermal conductivity. Wait, the electronic contribution of thermal conductivity. Yeah, he wants to measure that.
Mm-hmm.
But is that practical or is that just some theoretical stuff? Because would an experimentalist even try to separate those out?
Like why? Like why? Why did you do this experiment?
Yeah.
So I see how it could apply now. For example, Peltier coolers, where you apply a voltage to something and then you get a temperature differential.
Sure.
But I don't know if those existed back when this came around. When did this come around? It's got to be prior to 1902.
Yeah.
I don't see a date for this.
Right.
But I don't think Peltier electronics, I don't think they